square root. And a positive square root can not ever be equal to a negative number. So part of the point in having that negative, part of the reason I put that there was to kind of clue you in that, oh, there's no xyz points, there's no ordered triples below the xy plane, because the function is the positive square root. So it must be all above the xy plane. So that was part of why I put the -2. I didn't realize that only 4 people were going to recognize that a positive square root couldn't be negative. That did not occur to me.
It was a rough weekend.
It was a rough weekend. So on that problem, and then I felt a couple of things when I graded this problem. So a couple of things. A couple of non-positive things. Non-positive things. So
yeah, I'm feeling a couple of non-positive things.
You're feeling a couple of non-positive. So first off, I would hope by this stage of the game, if you see this, if you see that, I would hope that you would instantly know that that's the top half of a circle. I would hope that that's true. Is it true? When you look at that, do you see that as the top half of the unit circle? Like, no. So you want to get to the point where you see that, whether you do this part in your head or you actually write it out, it doesn't really matter, but you should be able to get to the idea that that's the top half of a circle really fast. That's college algebra level understanding of what this function looks like. So you want, whether you just sort of know it because you've done it so many times, that's fine. Or if you have to square both sides and add, that's fine also. So you know when you square both sides, this curve that you get will be a superset of the original curve. In other words, it can include more points. So this is just going to be the upper semicircle because y has to be positive because of how it's defined. So it's the upper semicircle. But you should be to the point, if you're not yet, practice these a little bit because you should be to the point where you see these types of things instantly. So if we had something like this, you should see pretty instantly that's the right half of a circle of radius, what? 2. Right? So you should, and again, if you have to, you square both sides and add. So you see, oh, superset, circle of radius 2 centered at the origin. Now let's go back and look at what our restrictions may be because we know there's a square root. X has to be non-negative. It's the positive square root, so this tells us that it's the right half. Okay, so that should be pretty comfortable to you being this far along in your math career. That is the analog of the circle thing. That's just a sphere. And so if you don't see it instantly, you square both sides. Maybe you want to call that z, and you add everything to the left side that is a variable. So you see that, okay, the superset is a sphere of radius 3 centered at the origin. Now let's go back and take a look at what this square root is restricting. Well, if we call that z, we see that z has to be greater than or equal to 0 because it's a positive square root. So that tells us of our superset, we're going to just take the points that have z greater than or equal to 0, which is the upper hemisphere. So, so that is one thing. That surface, and I'm emphasizing this because we're just about to be dealing with tons of surfaces and how they intersect. So it's going to be really important to recognize some of the more basic surfaces. And so then again, the other thing is that when you're looking for level curves, when you set this equal to a negative number, you should get no solution. So that's a clue, should be a clue that there's no part of the graph is below the xy plane. It's all got to be on top. So you're going to get a hemisphere. Yes?
So this was supposed to be like a full circle?
Yes. All the radius, or the domain, the domain for this is going to be all the ordered pairs that are inside the disk of radius 3.
Oh, and then it goes up.
And then the surface itself sits on top of that like an igloo. Top of that. Okay, so let's so look at the answer key. Email me or come stop by during the break, during my math lab time, and we can talk about anything you're not sure about with the answer key. So let's move on to double and triple integrals. We'll go with double first. So double the fun. Here we go. So first off, let's just think conceptually about a single integral. We want to have simultaneous to the technical math, I want to have the conceptual stuff going on. And if you see a single integral of a differential, what you should be thinking is that that's measuring the length of the interval. That's what you should be thinking. A single integral of a differential is the length of the interval, b minus a. So if you're not thinking that, start thinking that. And that's going to be very important when we start doing multiple integration, because there's going to be lots of times where we end up with the integral of a differential, and we don't want to be writing out this is equal to x from a to b, and then we plug in the b, and then we plug in the a. You don't want that extra stuff. You need that concept. It's like our reverse chain rule. Without reverse chain rule, you're doing not twice as much work, but you're doing extra work that is unnecessary. So just like reverse chain rule speeds up our efficiency, you've got to be able to look at a single integral of a differential as the length of the interval that's defined by the limits of integration. Okay, so that's what the single integral of a differential is. And then we think of the single integral of a function as area. So this one above we think of as length. And then we get area. If we integrate a function on an interval, we get the area between the interval and the function. So area beneath the curve. So that's our concept. Now let's jump to a double integral. We're going to have two analogs to this. We're going to see that the double integral of, I'm going to write this ahead of time. I'll write this as dy dx. They also will write this as just an area differential. And this is going to represent area of R. We'll talk about the details of that in a second. First, I just want to lay the groundwork for the concept. So double integral of a differential is going to be area. Double integral of a function is going to be volume. So just like the single integral, we're going to have analogs. Double integral of a differential is going to be, in its most basic sense, the area of the region that we're integrating on. Just like the length integral. We're integrating dx on the interval a to b. We get the length of the interval ab. Double integral on a region R of a differential, we're going to get the area of that region that we're integrating on. And if there's a function slapped in there, we'll get the volume beneath the function on the region R. So that's what they're showing here. The region R is down in the xy plane. We've got a surface defined above it. If we want to find the volume that sits between the xy plane and the surface, we do the double integral of that surface, and that will give us the volume beneath the surface on that rectangle R, or on that region R. It doesn't have to be a rectangle. So just like a single integral gives you the area beneath the curve, the double integral gives you the volume beneath the surface. So that's what our basic double integral concept will be. Double integrate a surface and you get the volume beneath it.
So pretty much you're integrating twice, essentially?
We will be integrating twice. Once with respect to x, once with respect to y. Yes, absolutely.
All right.
Okay,
getting
so
worried.
yeah. So we'll just do two single integrals in the long run.
Yeah.
The concept here then, to find the volume, the idea is that you partition that domain in the XY plane, whether it's a rectangle or some other object, you partition it into a bunch of little rectangles or whatever, little subregions. And then you pick a test value. All right? And then you imagine this parallelepiped, so this rectangular box that comes up, and that test value is going to be the height of that parallelepiped. And then we add up all the volumes of all the parallelepipeds, and we get an approximation for the volume that sits below the surface. Just like we did rectangles over here, here we do rectangular boxes, aka parallelepipeds, parallelepipedos. So add up all the volumes of those parallelepipedos, and you get an approximation for the volume beneath the surface. And the way we write that as a Riemann sum,
Oh no.
we won't use it though.
Please no.
We won't use it.
Please.
We won't use it.
Riemann is cool.
So here is the height. Yes, Riemann is
I literally
hyper cool.
He came really close to it.
because I hadn't done it.
So that delta A sub k means the area of that little rectangle down at the base in the partition there. So that's your delta A down there. So that's the area of the tiny little rectangle if we think in idealized terms. And then the height of the function at that dot, that gives us the height of our parallelepiped. Height times base area gives us little volume, the volume at.
Cool.
Yeah.
Okay, so I remember when we were doing stuff in Calc 1, we had like the left point,
Yeah.
the center point, and the right point, and the center point was x star k, at least
Yeah.
in the book that I had. Is this the same,
Same thing. This can
Just in
be,
the
yeah,
center?
the star point is any test point.
Any test
Any
point.
test point. Could be, so in Calc 1, it could be the left, the right, the center, any test point. And it didn't matter because you let the interval go to 0 in width, so it didn't
Yeah.
really matter what the test value was.
Norm of
Same
the
idea here. Now here we can't even talk about left endpoint, right endpoint. It doesn't make any sense.
No.
So here
Have to use
we're just,
Cartesian coordinates.
yeah, we're not, so all we imagine is that star point is any point in that little sub-rectangle down there. And then we figure out the z value at that point. But again, it's all conceptual. We're not going to do any problems where we use a Riemann sum here. It's way too complicated. So the z value at the star point is the height of the parallelepiped. Delta A is the area of the base of the parallelepiped. Multiply the two together, you get the volume of that parallelepiped. Add them all up, and you get an approximation to the volume beneath the surface. Then we make our definition. So we all know that when you take the limit of a Riemann sum, we define the output of that to be an integral. So in this case, we're going to define that to be a double integral. So the double integral of the function f with respect, so this differential here is an area differential as opposed to a length differential like dx or dy. dx or dy is a little differential in x. It's a one-dimensional differential. This is a two-dimensional differential. You think of it as a tiny rectangle. And if you take the limit, as the magnitude of the partition goes to 0, you get the integral. So that little symbol there, that delta right there, that means the magnitude of the partition. Again, this is theoretical. You were never going to use it. But the concept is that if we have our partition down in the xy plane, so we're imagining a bunch of, in practice, you do not have to make this a regular partition. The rectangles can be of different sizes. So let's suppose this is our partition. In practice, if you were going to try to do this by hand, of course you'd use a regular partition. It'd look like graph paper, right? You'd make every width the same, every height the same of all those little boxes. You know, why make them all different? But the definition of the magnitude of a partition is the longest diagonal. The longest rectangular diagonal is the magnitude of the partition. And so what we want to do is force all the little rectangles to go to 0, just like in Calc 1 we forced all those little subintervals to go to 0. So same idea. And in Calc 1, your partition with subintervals didn't need to be regular. You could have, you know, all sorts of different widths for your subintervals. But as long as you said all of them, the largest one is going to go to 0, then you're fine. Same idea here. If we say that the largest of the partition rectangles is going to go to 0, then we're fine. So in your mind, you can imagine those parallelepipeds getting smaller and smaller bases. So the approximation up underneath the surface gets closer and closer. And if you take the limit and let the partition go to 0, you will get the exact volume that sits below that surface. And like I've been alluding to, this is painfully difficult to use. In two-dimensional space, two-dimensional domain, there's a million test points you could pick, trying to come up with some scheme to pick your test values. Virtually impossible. With one variable calc, you can say, yeah, choose all the left endpoints, or all the right endpoints, or all the center points. You can't. There's no analog that you can do quite so easily when we're dealing with a two-dimensional domain. Okay, so the first real theorem that we're going to deal with here is Fubini's theorem.
It's the best name.
Fubini.
Is that
Fubini is going to allow us to evaluate. So Fubini is going to take this right here, which is called a double integral. So we need a way to evaluate a double integral. And what Fubini says is that you can do this. You can do a partial integral with respect to x first, and then do a partial integral with respect to y second. In other words, we can do what Will said, integrate twice. Bless you. So this first integral here inside is a partial integral with respect to x.
And pretty much we're just using the same logic where you've been using for partial derivatives. Just treat the ignored variables as constants.
So if we're partially integrating with respect to x, anytime we see a y, we just treat it like it's a constant. Yep. Exactly.
Yep.
And when we have as our domain, so the simplest type of domain down in the xy plane is a rectangle. And when we have that simplest domain in the xy plane, a rectangle, it doesn't matter whether you put the y limits on the inside or the y limits on the outside. You just have to make sure that you line up. If you put the y limits on the outside, then the dy is on the outside. If you put the y limits on the inside, then the dy is on the inside. You just have to make sure those line up. But with a rectangle, it's interchangeable. It's not going to matter.
Although it's something like a circle, things get a bit more complicated.
So when we have a domain that's not a rectangle, when we have curved boundaries, it will matter. We won't always be able to just switch. So when we have a domain that's nice and simple, like a rectangle, it doesn't matter. We can just switch. We can put the x's on the inside or the x's on the outside. And it's Fubini that allows us to take this double integral and break it into what this is called is an iterated integral. So an iterated integral is where you integrate one at a time. So we're going to see the same type of thing with a triple integral. We will iterate them. We will integrate once with respect to x, once with respect to y, and once with respect to z. So Fubini says take a double integral and break it into two singles. So you should see this as one symbol here. The double integral with the r, you should see that as one double integral, whereas over here you should see that as two single integrals. So let's go ahead and do some math with some partial integration. So here we go, partial integration. All right, so first we're going to do the inner integral. That's with respect to y. So every time we see an x, if we're integrating with respect to y, we treat that x like it's a constant. So we are going to have the outer integrals floating, weighting. So the inside integrand integrate with respect to y, we will get 3x squared y plus y to the fourth. And then the limits of integration are 0 and 1. And then we have our dx. So that is the partial integral with respect to y. Everybody agree? So we're thinking of that x as a constant. So 3x squared is a constant. 3x squared is a constant with respect to y. And if you integrate a constant, you get that constant times y. All right? So that's a partial integral. And then we evaluate the inside. We just leave the x stuff alone. So we have to be very clear that these two numbers here, those numbers are being plugged in for y, not x. Those are y limits. So when we plug those in, we just have to be thoughtful. First, we plug in 1 for y, and we get 3x squared plus 1. And then we subtract off 0. And so that second part just goes away. We have that. And now we're back to basics. We've got a single integral with respect to x, and there's no weird extra letters in there. It's just a typical scenario that we're very familiar with. Plug in the 2, we get 10. Subtract off 2, so we get 8. So that is representing the volume beneath this surface. Bless you. Z equals this integrand is a surface. We're restricting our attention to this rectangle down in the xy plane, so this integral right here is finding the volume beneath that surface on that rectangle. Now, of course, the same thing that happened in Calc 1 is happening here. You can have signed volume. You can have signed volume if your surface goes beneath the xy plane. So we all know from Calc 1 that if we integrated this function straight across, we would get this upper area minus this lower area, right? The integral would be whatever is above minus whatever is below. We call that signed area. So if you integrate a function that's symmetric on your interval, you would get 0. And if you integrate the cosine function from 0 to pi, you get 0. Because there's just as much area above as below. If you integrate sine from 0 to pi, you get 0. So same thing is true with surfaces. If your surface goes below the xy plane, you're going to get the volume above minus the volume below. You get sine volume.
How do you know that that's a rectangle?
So this tells me that y is going from 0 to 1, and x is going from 1 to 2. So if we were to take a look at that domain, so y goes 0 to 1, x goes 1 to 2. So we are dealing with this rectangle right here. That's the domain right there. That's what we would call the region R. So the quick and dirty way to figure out that you're dealing with a rectangle is if all these are numerical, then you know it's a rectangle. So if all 4 of those integration limits are numbers, then you know you're integrating on a rectangle. If one of them is a function, then your integration region is going to be different. It's going to be curvilinear. It's not going to be a rectangle.
If you try to do your integrals in different orders, but you switch your, like if I wanted to start with dx, can I switch them and it'll still give me the same result?
Yep. So if you switch, as long as you switch your differential and switch those. So as long as you keep your y limits with the y, your x limits with the x, you'll get the exact same answer. So if you integrate, if you want to go with respect to x first, then you'd plug in the 1 and the 2 first, and then integrate with respect to y, and then plug in the 0 and the 1.
Is that true with functions?
Yep. Well, to a degree. To a degree. We'll look at some examples very shortly. Okay, so number 12. Integrate this with respect to y. So we ignore the x and the x limits on the outside. We just look at the inside. Integrate that partial integral with respect to y. Treat the x's as constant. So the outside integral and its limits just come along. We're going to integrate this with respect to y. Okay, so the x on the outside is just a constant. The derivative of the inside with respect to y is x. So we're going to do this partial integration like this. Everybody follow that? So the integral of cosine is sine of the exact same angle, but we don't just have a y, we have an x times y, we have a constant times y. So the reverse chain rule says partially differentiate the angle with respect to y. The partial derivative of this is x, so we have to reverse chain rule it and divide by x. Those guys will cancel, which is great, because when we first looked at that, we see, oh no, integration by parts. Right? We see the x on the inside and the x on the outside of the cosine function. Normally, we would say that has to be done by integration by parts. So this is a great example where you would not want to integrate with respect to x first unless you love the voodoo. If you love doing the voodoo, you could do it with respect to x first, but it's going to be a lot more work. Will?
Yeah, so pretty much we can't just treat x as a constant in this case, like we can't treat it as if it were 2 or something.
Well, we are doing that, though, aren't we?
True.
Oops, I forgot to evaluate this properly.
I know, it's been a while since I've done
So we are treating it just like it's a 2, right? If this was a 2y, we would divide by 2, right?
We haven't integrated for like months. So.
It may feel like months. So now we plug in, and remember that we're plugging these in for the y, so we're going to get sine of just x minus sine of 0. And what is sine of 0? 0. So we end up with that.
I like
nice.
it. I like it.
Yeah, that's pretty cool. Works out very well. So, and what we're going to be learning then is what's the most efficient way to do a double integral, or to do an iterated integral. Should we do it with respect to x? Should we do it with respect to y first? Yeah, we're going to have to figure it out. All right, so cosine of pi over 2 is 0. Cosine of 1, cosine of 0 is 1, so we end up with 1. So again, conceptually, what you're thinking in your mind is that we have some surface right there. And if we just imagine that the surface is above the xy plane, then that's telling us that the volume beneath the surface on this rectangle is 1 unit, 1 cubic unit.
I have an unrelated but burning question.
Burning question.
Do the highlighter colors on there mix if you go over them with one another?
You mean like that?
Yeah.
You must be taking physics.
No, I was just curious.
Omar?
Would it be -1?
Well, when we plug in the pi over 2, we get 0. So it's going to be 0 minus minus.
Drop
Yep.
negative.
Yeah, no problem. Other questions on it?
So when you have bounds, you evaluate and then intercept.
Yes. So we treat the first integral
So you do it
completely,
and
then we do the
second.
outer integral.
Okay.
Yep.
That's fine.
That's right. That's exactly right. All right, here's one. Limits of integration are pretty easy here. So we can, again, we'll do the partial integral with respect to x first. We'll keep the y's for later. We're going to do that part. So the y that's sitting in there is just a number. Think of it as a number. So we're going to get that number multiplied by the integral of 1 over 1 plus x squared, which is inverse tangent of x. That goes
Oh my gosh.
You warned us, we need to know it.
Yeah.
That looks really nice, right?
Well, yeah.
Yeah, that's good.
Yeah.
So then we totally evaluate. These are now x limits that we're plugging in. So we have y times the inverse tangent of 1. That's the angle on the right-hand side of the circle with a tangent value of 1, which is pi over 4, minus the angle on the right with a tangent value of 0, which is 0. Yeah. And so the pi over 4 can pop out in front as a multiplier. And then we integrate just y. So we get y squared over 2. And that gets evaluated also 0 to 1. So we end up with, looks like pi over 8. Pi over 8. So again, conceptually, you're imagining that as the volume beneath this surface on that square, 0 to 1 in the x direction, 0 to 1 in the y direction, that unit square. That's the volume of this surface, volume beneath this surface. And with all of these, it will not matter, again, when you have numerical limits of integration. We could have integrated with respect to y first, got y squared over 2. The 1 over 1 plus x squared would be constant with respect to y. We get the same answer. Doesn't matter. All right, another one. So here they've given it to us as a double integral, and they want us to write it as an iterated integral. So we want to break it into two singles. And again, it doesn't really matter in this case which we want to do first. Do you care? X first? Doesn't matter. Both will be about the same. So we'll do that. So x we put on the inside, so that means we have to put the x limits on the inside. We just have to make sure that the differential lines up with the correct integral. So the outside and the inside. So these two go together. Those are the outside. And then these two go together. Those are the inside. So if we integrate with respect to x, what function is that?
Sine inverse.
Inverse sine, good. So that's going to be y times inverse sine of x. So the y is constant with respect to x, so that just comes along as a multiplier. And the integral of 1 divided by root 1 minus x squared is arc sine. Put our limits of integration. We have that. So we evaluate inverse sine at each of those endpoints. So we end up with integral from 1 to 2, y. Inverse sine of root 3 over 2. That's angle on the right with a sine value of root 3 over 2. Pi over 3. Somebody said pi over 3. Inverse sine of half. Pi over 6. Angle on the right with a sine value of 1/2. We still have our dy. Pi over 3 minus pi over 6 is pi over 6. 6. Integral of y is y squared over 2. 1 to 2. So we get pi over 12 multiplied by 4 minus 1. Pi over 4. Cubic units.
Unit circle is important.
Yes, unit circle is very important. Yes,
Would
we use it a lot more in Calc 2 and Calc 3 than we did in Calc 1.
we be more likely, like on a exam, for you to have us like show us like this with the set, and then we have to like set it up for evaluation, or would you just give it to us like the other ones?
Either way. Either way. On an exam, we're going to go so far beyond this that these probably aren't even, wouldn't even be exam questions.
Okay.
Because we're going to, the bigger issue is when we have limits of integration that are functions. That's going to be where we're going to spend the bulk of our time.
Okay.
So the simplest ones are when they're numbers. When they're numbers, that's kind of...
Well, I know that. I meant like, even if they were like functions, like would you give it to us like this and we have to set it up to evaluate?
So if they were functions, it could be either or.
Okay.
Yeah, either or. We'll see that there's going to be lots of times where you have a picture and you have to decide which way to go. Yeah. All right, any questions on the mechanics there? Inverse sine good, inverse sine gone. Okay, another one. Again, you look at that and you can integrate with respect to x or y first. They're both pretty reasonable. It may feel better to get rid of the y first, just to get it out of there before we try to do a substitution with a y coefficient that will work. So again, it doesn't really matter, but I would say let's get rid of the y first because we see x showing up in 2 places. So maybe if we go with respect to y first, maybe one of the x's will disappear. It's possible. It's not going to happen in this case, but spoiler. Good.
Are we ever going to have a situation where if you integrate with respect to one variable first, you're going to get an impossible function?
Yes.
Oh, okay, good.
Yes.
Will it happen in a rectangular
That's the way I
one?
like it.
Yeah, there's absolutely going to be times where you have to do it one way.
Got it.
The other way just won't work. Lots of times where it can go either way, but many times where you can't. Yeah.
Can we do integration by parts?
We don't need to here, we just use substitution. Because the x on the inside is squared, So if we let u equal 2x, it's going to absorb the x on the outside.
But can we? Like, if
Oh, can you?
Yeah.
Oh, you can. You know, that's a good question.
Okay.
Yeah, test it. Let me
Okay.
know. I mean, so do you agree that substitution would make more sense there because that square on the inside? The piece that's going to be hard with integration by parts here is that if you let u be this sine thing, you're going to end up with a product.
Right.
Because you're going to get cosine of x squared times 2x. So that's going to make it more, it could make it more complicated.
It looks like something that you could.
Now, if there wasn't that 2 there, then absolutely. If there wasn't the 2.
If we integrate by with respect to x, we get negative cosine of x squared divided by 2x, right?
Mm-hmm.
And the x outside will cancel.
Yep. Yeah, that's true. If you let it go with the integral, if you did the dv equals sine of x squared, you know, that could, yeah, it probably will work.
Okay.
If I can avoid integration by parts, I usually do, if there's something easier. But it's a really good question. Could we do it if we didn't notice? And we just went ahead and did it. All right, so let's integrate with respect to y first. So we're going to have x limits are going 0 to square root of pi over 2, all in the square root. And then the y limits are 0 to 1, so we're going to put those on the inside. So we have that. Integrating with respect to y, so we're doing a partial integral. Everything else is waiting. Integral of that with respect to y, we get y squared over 2. So those limits again are for just the y. So if we plug in 0, it all disappears, so we just have to worry about the 1. We're going to have our outside integral. Inside, we're going to be left with x over 2 times sine squared. Not sine squared, sine of x squared. Definitely go with u sub. So let u equal x squared. Du will be 2x dx. So x dx will be du over 2. And let's see what we end up with. We will have, looks like we're going to end up with sine of u all divided by 4. And then we'll deal with our limits in a minute. Integral of sine is minus cosine. And then we got to get back, so that's going to be minus 1/4 cosine of x squared. Limits on x squared are 0 and square root of pi over 2. And that should be good. All right, plug in square root of pi over 2. We square that. Cosine of pi over 2 is 0. And then minus a minus. So we get plus 1/4.
We have the minus sign outside.
Say that once again.
We have the minus sign.
Oh, is there more than one minus sign?
Well, because isn't it minus a minus?
Which is why we got a plus.
Right.
Do you agree with that, hon?
I think it's negative 1/4.
Anyone else think it's negative? We had.
Oh yeah.
It would be 0 minus.
Good.
Minus 1.
All right, he's got.
Stands alone.
He has conceded.
Lone Ranger.
Yeah.
Can you revisit real quick if we wanted to change our boundaries then?
So if we wanted to change our boundaries, we'd look right here. So if we wanted u limits, we'd have a 0. And if we plug in that squared, we'd have pi over 2. So we could go right here, 0 and pi over 2, which absolutely would work. That might, in fact, be easier in this case. It might be.
Plug it into the U though.
Plug it into the U, though. Right. Exactly. Plug it into the U. All right, here we have another one. Here they say choose a convenient order. So here the y on the inside is not squared, so that's definitely an integration by parts if we go with respect to y first. So here's where we would say, well, let's go with respect to x first then and see. Maybe going with respect to x is going to help us. Maybe it will somehow eliminate the need for integration by parts. Maybe. Maybe not. But maybe. So we'll go with respect to x first, just because we know we won't have to integrate by parts. That gives us the following. Integral of cosine is sine of the same angle divided by the derivative of the angle with respect to x. And when we differentiate that angle with respect to x, boom, there's a y. So that's going to cancel the y out in front. So we're golden. Now we don't have to integrate with respect to, or we won't have to use integration by parts. So let's simplify what's inside before we integrate with respect to y. We're plugging those limits in for x. So sine of y minus sine of 0. Sine of 0 is 0, so we have no other term. We just have that. Minus cosine of y. Cosine of pi over 3 is 1/2, so we get negative 1/2 plus cosine of 0, which is 1.
Question?
Yeah.
Shouldn't we have gotten negative sine of x, y when we integrated the first time because we integrated cosine?
Integral of cosine is positive sine because derivative of sine is
Oh,
cosine.
yeah, sorry.
Yep. It's very easy to get those tangled up.
Especially when you're doing substitution.
Substitution. Yep. Shrink functions. All right. One more rectangle here.
I don't think we'll be so lucky this time.
You don't think we'll be so lucky this time? Let's see.
Yeah, what was the answer to the last one? 1?
So the other 1/2 was our final answer. Right? We had 1/2 as our final answer because we had negative half plus 1.
It's not the same problem.
Okay, so, no. All right, so we've got that thing. Same idea, though. If we see the y's look kind of messy, let's go with respect to x and see if that helps. So if we go with respect to x first, the x limits have to go on the inside then. The y limits will go on the outside, so that's 0 to the square root of pi over 2. And then our function, our surface. That's our surface. And we said that we're going to do x first, so this is going to be dx dy. All right, integral with respect to x. So partial integral with respect to x. Those y's are just constants, so we'll just put them in there. They're coming along. The integral of sine is minus cosine, so we definitely get a minus here, of the same angle. Then we have to differentiate the angle with respect to x, divide by it. Like that. Okay, we're plugging these numbers in for the x's. The y's are constant with respect to x. So we end up with minus y cosine of 4x, excuse me, cosine of 2y squared minus a minus is plus y times cosine of 0, which is 1. Do you agree we end up with that?
You just divided out that, yeah.
So those go away. Minus y cosine of 2y squared. Subtract off what happens at 0, plug it in for x. Cosine of 0 is 1, so we get minus a minus 1 times the y.
And now we do substitution.
Now we're going to do u sub for the first part. The second part we can do straight off, but the first part we're going to let u equal 2y squared. So du will be 4y dy. 4y dy. We'll rewrite this. And let's see. This time, let's go ahead and change the limits. We didn't do that the last couple times. Let's do it this time. So if y is 0, then u is 0. And if y is that thing up there, we square it, we get pi over 2 multiplied by 2 is pi. So those will be our u limits. And let's see. So that part right there becomes cosine of u. And then we have y dy, which becomes du over 4, but it's negative. So negative, that's one way to write it, I guess. So that's all the first part. We'll deal with the y in 1 second. Does everybody think that's okay? Cosine of u. Solve this for y dy, that's du over 4. So y dy becomes du over 4, and the minus has to carry along. Let's deal with the y now. This we can integrate straight off with respect to y. So that's going to be y squared over 2 with limits of 0 and square root of pi over 2. We end up with minus 1/4 sine of u from 0 to pi plus pi over 4. No. Yes. Pi over 2 divided by 2. And I think that you're right, because when we plug in pi here, sine of pi is 0, sine of 0 is 0, so this all becomes 0, and we're left with pi over 4. And whenever you get 0, you should ask yourself why. And if you look right back here, we integrated cosine. Forget about the minus 1/4. If you integrate cosine from 0 to pi, doesn't that give you 0? So if you were paying attention, you could probably jump to the answer right away, because you know that cosine from 0 to pi looks like this. So there's 0, there's pi, there's just as much area above as below, so you get 0. So whenever you're doing an integral and you get 0, that must mean there's some symmetry that, you know, maybe you should be paying attention to. So if you integrate that function on that interval, that's all going to be 0. All right. Average value theorem. Makes perfect sense to ask about the average value of a function. So back in two-dimensional space, remember in Calc 1 you had an average value theorem. In Calc 1, you would find the average value, and maybe it's right there. And the idea is that this red area, if you basically, it's basically that sand type of thing, where if this was one of those sand machines and that's your function, you shook it and then all the sand comes down and creates a perfect rectangle there. So the area beneath the curve is the same as the area of that rectangle. So the average value is whatever that height is right there. That's your average function value. So the average function value is the height of the square, or the height of the rectangle that's going to give you the same area as beneath the curve. Over here, now we're talking about surfaces. So we've got some undulating surface. We want to figure out the average height of that surface so that we have a parallel pipette that has the same volume as the volume beneath the undulating surface. Right, so if we had this big surface, and it was a big sand castle, we'd shake it and figure out what the height of the parallel pipette is. So the average height, just like over here, you would find the area beneath the curve and then divide it by the length of the base to get the average height. Same idea over here. We're going to take volume, so this right here is volume. And if you do volume divided by the area of the base, you're going to get the average height. Volume divided by base gives height. Volume divided by base gives height. And that's what this theorem is telling us. It's giving us that symbol, that little bar on top of the F means the average F, the average function value. So we do the volume divided by the area of the base, and that will give us the average height. So let's try one. Compute the average value. So first, let's find the volume beneath this plane. So we have a plane. It's defined on that rectangle, and it doesn't matter when we have limits that are constants. It doesn't matter which order. Oh, these doesn't matter at all here, since they're the same. So this is going to give us the volume beneath the surface and above that rectangle. So integrate 0 to 2. We're going to integrate with respect to x. So we get 4x minus x squared over 2 minus x times y. dy 0 to 2. So integrating with respect to x, the y is a constant. Plugging in those limits for the x values. Plugging in those for x gives, so this stays alone. Let's see, 8 minus 2, so that's 6 minus 2y. And you plug in the 2. And then we plug in the 0 for x. Everything goes away, so this is all that we're left with. Integrate that with respect to y. And we get 6y minus y squared, 0 to 2. So we get 12 minus 4, which is 8. So that's the volume. So right now we have a tilted plane. That's what our surface is, a tilted plane. And we just found the volume beneath it on top of that rectangle from 0 to 2, 0 to 2. So tilted plane. Now we need to find the area of the base. And what is the area of the base?
Is it the 1 over part?
So that's the part that's going to be the denominator. And the base, we go 0 to 2 in the x direction, 0 to 2 in the y direction. So the area of that rectangle is 2 times 2, which is 4. So this tells us the average value then is going to be 8 divided by 4, which is 2. So the height of the average value is 2. So that parallel pipette of height 2 has the same volume as the volume beneath the tilted surface. So just like that.
You found the 2 times 2 based on your limit?
Based on the limits of integration.
Okay.
So this is based on the fact that we're down in the xy plane and we are dealing with that as our region. Mm-hmm. Oh, good. Perfect timing. Time for a break. So this is sort of the preliminary section. This is the springboard. The springboard.
So, dancing, and I
The
got
table is set.
I'm gonna do some more of these, but I don't want to.
So
Do you want
I want to see tennis
13.2.
balls right in the
Show
middle
your
of,
fingers on it?
of one of the new motions, except that there's already been generated in 1.12.
is where we're going to up the ante a little bit. And instead of having a rectangle as the domain, we're going to have curved boundaries. So we need to figure out then how to treat these more complex integration regions. Now, one thing that is going to be true is that we have to at least have one set of limits that is a set of constants. If we want to end up with a number as our answer, if we want to find the volume, we want a numerical value, we're going to have the outer integral have numerical limits. Now there is another type of integration. If you go way on in math, there's another type of integration that you can use on a boundary that's got weird, everything is weird, that there's not one set of limits, one set of constant limits. There's a type of integration called the Lebesgue integral for really complex regions. A Lebesgue integral is a generalization of this integral, which is much more complicated. We'll be sticking with the easier integrals, but we do need our outer integral to have numerical limits or we won't end up with a number. So that's one of the guiding principles, is that if we have curved boundaries, we want those curved boundaries to represent the inner variables' limits of integration, not the outer variables. So these outer variables, those we want those to be numerical for this to work. So let's go ahead and take a look at what we mean. So I call them vertically oriented or horizontally oriented. And if we take a look, we've been doing this, we've done this in several different contexts of integration, but we would call I would refer to this as vertically simple or vertically oriented, because a vertical element will be consistent all the way across the region. We'll have the same upper curve and the same lower curve, whereas if we drew a horizontal element, we're going to have different scenarios depending on where we draw it. Different left curves and right curves. It's a total mess. So we would not want to use a horizontal element for that region. We'd want to use a vertical element. Similarly here, a vertical element makes the most sense. Similarly here, a vertical element makes the most sense. So we want to choose the element that has a consistent upper and lower curve. What's that?
It's coincidence how we got 3 of the same kind in a row.
Yeah. Let's see what happens down here. Oh, look. And so these are horizontally simple. These are horizontally simple because you have a consistent left and right curve. And if you were to choose a vertical element here, it'd be a total mess. You'd have to subdivide, and you don't want to do that. Yeah?
So you're saying like when we did this in Calc 2, you could do it either way, but you had to find where they intersect. You're saying that's going to be really brutal? Okay.
Yes. Yeah. So like right here, if we wanted to use a vertical element, in this one we'd have to split it here, and then you could use that region, but then over here it's going to intersect itself.
Are we not going to encounter places where we have to do that? Where no matter either way, you're going to have splits?
I don't think we may encounter somewhere where you have to split it into 2 regions maybe, okay, but nothing unmanageable.
Okay.
For the most part, there's already so much going on. For the most part, it's going to be either vertically simple or horizontally simple. Okay, so let's try one. You have to draw your boundary curves here. There's no way around it. And if you don't draw your boundaries, you will not be able to discern what the limits of integration should be. So this is where you have to be able to graph.
Dang it.
So you have to be able to draw your boundary curves, and it's just going to get worse. So from here on out, if you can't draw your boundary curves, it's a problem. Because the limits of integration, you can only really tell if you look geometrically and see, oh, which curve's above the other curve, which curve is to the right, which curve's to the left. So you're going to have to be able to graph your boundary curves. Now, these are just lines, so don't panic. So this says boundary x equals 0. So x equals 0, that's just the y-axis right there. And then we have y equals 2x plus 1. And we don't have to be super precise. We know the y-intercept is 1, and we know the slope is 2. So that's going to go up something like that. slope 2 with a y-intercept of 1. And then this one, y-intercept of 5 and a slope of -2. So we don't have to be super precise, but we need to be able to tell the relative position of each of those boundary curves. We need to know which one's on top, which one's to the right, which one's to the left. So this will be our region in here that we're talking about. That's the region that's trapped by all three of those curves. So this curve right here is y equals -2x plus 5. This is y equals 2x plus 1. All right. So should we choose a vertical element or should we choose a horizontal element? Definitely a vertical. We'll have a consistent upper and lower curve. Now this is a case where you could choose a horizontal element, but you'd have to subdivide it into 2 regions. But you could do that here. You could find that intersection point, but who wants, we're already doing a double integral. Why do you want to do a double integral twice? Let's just do a double integral once. Let's not do that. Not yet. We'll do that later.
Yet.
Not yet. We'll do it later. Later. Okay, so let's set up our double integral.
Don't we need to find something first before we
Say again?
Don't we need to find something before we set up our integral?
Like
a second x bound?
You mean the intersection point?
Yes.
Yes, we will have to find the intersection point. Absolutely. So our surface, though, we can put that in, and we've chosen our order. Which order should this be?
dy dx.
So this should be dy dx. The vertical element is going between these 2 functions, the 2 lines, and then the x interval is our constant interval. So our x interval, we are moving left to right from right there over to whatever that intersection point is. And so the x variable is the constant variable. It's the variable that has constant limits of integration. So there's an element for all those x's between 0 and whatever that intersection point is. Okay, so that's why we know that the x's are on the outside, because there's a vertical element for all x's in that interval. So the outer limits will be the x limits, 0 to whatever the intersection point is. The inner limits, that element goes from 2x plus 1 up to minus 2x plus 5. So when we look at this element, we have to go figure out what the lower y value is and what the upper y value is. This is the y value at the bottom of the element. That's the y value at the top of the element. So it's just like we used to find area of upper curve minus lower curve. It's that same type of thing. We go lower curve down below, upper curve above. And let's go ahead and do what Omar suggested. He said, let's figure out what that intersection point is. We don't know what this x value is yet until we solve this equation. So we see that that x value is 1. So we have to do a little computation to figure out what this point is right there. So that point right there has an x value of 1.
So
Yeah?
that's our upper limit.
Mm-hmm.
Okay.
So our lower limit is 0. So when we integrate horizontally, we always go left to right. So the x value there is 0, and we're going to integrate to the right up until we get to 1. So the inner integral has the functions. The outer integral has constants. So now let's do our partial integral with respect to y. Actually, let me move that over here. We're going to need space. So integral 0 to 1. Inside here, we integrate with respect to y. So we get y squared over 2. So we're going to get x, y squared over 2. And now we've got to plug these functions in for y. Yeah?
So you said that, so the y integration is top to bottom, like it's always been. But the horizontal is left to right instead of right to left?
We always go left to right for horizontal and lower to upper for vertical.
Lower to upper. Was it different in Calc 2?
Nope.
It was subtracting the top from the bottom, right, and the right from the left. So
Yes.
Is that what you're saying? I'm just not.
Yeah, so
Okay.
if we're trying to find a vertical distance, it's always upper minus lower. And if we're trying to find a horizontal distance, it's always right minus left.
Okay.
And if we're looking at the integral symbol for if it's a vertical integration, it's lower to upper. If it's a horizontal integration, it's left to right. So it's always left to right, lower to upper.
So, I guess I just wasn't paying attention or something. Where did the xy come from in the interval?
Right here,
Nope.
here,
Yep.
that's given.
It's given? Okay.
Yeah, so that is the function, that's the surface. So that's the surface that we're integrating to find the volume under it.
So if we have our point of intersection, why can't we just plug that in for x and solve for x and y and integrate without functions? Just, you know what I'm saying? You have the integral there from 2x plus 1 to negative 2x plus 5. We have the point of intersection, so why can't we just plug in the number there?
So the idea is this. So you're imagining the surface sitting on top of that triangle, right? And we have to figure out what we're imagining with that red element is that we're taking a cross-section of the surface and what's beneath it. So a cross-section of the solid object. So our surface is sitting here, and we're going to have these little slices, each of which have a different area. So we have to have limits of integration here that are functional because they're measuring what the base of that corresponding cross-section is. Can you see that? So we've got our surface up here, and then we're doing all these cross-sections. But the cross-section, the cross-sectional base is going to change, right? This red element's going to get longer and longer as we move to the left, or shorter and shorter if we move to the right.
Okay.
So the reflection of the fact that every cross-sectional area is changing is right there. Unlike solids of revolution. Solids of revolution, remember, we could cross-section and we could get an area of a disk or a washer. And so that all boiled it down to the cross-section being a function that we only needed one variable to represent. Here, each cross-section, we need the x's to give us the area of the cross-section at x.
Okay.
And each of those cross-sections is going to change. So we're basically, this inner integral is giving us cross-sectional area right here. This, including those dy, this gives us cross-sectional area. So when we get over here, let's go one more step. Then we're going to be back to where we were with solids of integration. Let me show you. Let's do one more step, and then I'll tell you what I mean by that. So we're going to have integral 0 to 1. So now we have to multiply all this garbage out. We have to square it. We have x over 2. We have to square that thing, so we get 4x squared minus 20x plus 25. And then we have to subtract off what we get when we square the lower thing. So that's going to be minus 4x squared minus 4x plus minus 1 dx. So this, let me go one more step, and then we'll talk about the interpretation of this and how it relates to the solids of revolution that we've already dealt with. So we're going to deal with this. Oh, the squares cancel. That's nice. And then we have minus 24x squared divided by 2, so minus 12x squared. So we took care of that one and that one. And then we just have to deal with our constants. So plus 24 divided by 2 is 12 times x.
Isn't it just x, not x squared? Minus 24x.
Oh, why did I put it? Yeah, why do I have a square on that thing?
Because the
I think you like.
I distributed this
integrated
x. This x.
Oh.
That x. Yeah. So it's minus 24 times x. So, yeah, that. And then this constant is getting multiplied by that x over 2 also. Okay. So now we're in the analog place to where we were with solids of revolution. With solids of revolution, we found our area as say a function of x. So if we were doing a rotation about the x-axis like this, let's just suppose this function is 1 over x, then the radius was 1 over x, and we said that the area of the cross-sectional disk is pi times r squared. So we get pi over x squared in this case. That's where we are right now. This is the cross-sectional area at x. So wherever the x is here, if you imagine this element that I've drawn, and you imagine that x, and you imagine the surface sitting, we're to slice through that solid object right down to that, bless you, right down to that red element. This function is telling us that cross-sectional area with respect to x. So when x is 0, cross-sectional area is 0. When x is 1/2, as we start moving across here, we're going to get all of our cross-sectional areas. And then we add them all up, and we get our volume. OK, so now we're almost there. Integrate this with respect to x. We get minus 4x cubed plus 6x squared, 0 to 1. And I think that's just 2. All right, so that is the volume beneath this surface. So the surface is z equals xy. It's something over here sitting on top of that triangle. That's now the volume that sits between that triangle and that surface.
Why couldn't you switch your dx and dy? Because why couldn't you integrate by x first?
So you can't integrate with respect to x first because the limits come along with the differential. So if we put the y on the outside, then these things would have to go on the outside, and then we wouldn't end up with a number. To get a number, you need constant limits of integration. So at the very end, you can plug them in.
Okay.
If you don't have constant limits on the outside, you're going to end up with a function,
That makes sense.
not a constant. Just like in here, we don't have constant limits of integration here. So when we do this integral, we end up with a function. Right? So if we have variable limits of integration, when we calculate the integral, we end up with a function of whatever that variable is.
Might be a bit ahead of myself, but let's say that you had the function on the outside, then you were going to end up with the function at the end. Does that mean that you could have some constant of integration that would be a function? Like how we have here, if we just had the indefinite integral of this, you know, there'd be some constant plus c, which is a number. But if it was a function, would that constant also turn into a function of?
Yes.
Okay.
Yes, and we will see that when we start to try to rebuild from a partial derivative to build up to a surface. We're going to do a partial integral, and that constant of integration will actually be a function. Yes. So that's right.
So when you're choosing your element, does that dictate which order?
Yes.
So like when you were doing shells or discs or whatever, it was dy if it was vertical first, and then dx if it was horizontal. Is that what you're saying?
Yes. So here, when we choose a vertical element here, that means that the dx is going to be associated with it is going to come from the constant interval. So if we have a vertical element, then dx is on the outside, dy goes first, and dx will have limits that are constants. If we choose a horizontal element, it will be reversed. So if a horizontal element, that means that the y's are going to be constant, and those have to be on the outside.
Sorry.
No, that's exactly, it's true. Okay. Yeah, the shells are a little different because you had a little bit of each.
I was thinking about it in like when we were rotating solids.
So like
that's the other
here,
side
when we have a vertical
decided-
element, we go around the x-axis, we get a disk, and we use a dx.
Yeah.
So
Yeah.
it's always good to think of the thickness of the element as being the thickness of that element is dx. Horizontal element's thickness is dy. Okay, so here we have another surface.
Did you mean to skip one?
Yeah.
Did I skip one?
Yeah.
Oh, thank you. Good point. Okay, another set of boundaries. We've got to draw those, or there's no sort of way around it. You can't not draw them. There's not really a good way to understand what's happening if you're trying to switch your limits of integration unless you can draw them.
Yeah, they don't need to be really good drawings, just generally
Rel-
sort of the scale.
Yeah, relative sketch so you know what's on top, what's on bottom, what's left, and what's right. Okay, so x equals 1. That's just a vertical line. Y equals 2x plus 2. So that's a slope of 2 and a y-intercept of 2. Move that over a little bit. So y-intercept of 2, slope of 2, something like that. And then negative x minus 1. So negative 1 is the y-intercept, and the slope is down. Slope is negative 1, so it's going down to the right. So something like that. So that gives us a relative sketch. So it tells us how everything is oriented. This is x equals 1. This is y equals negative x minus 1. And this one is y equals 2x plus 2. And now there's no other bounds here. So what we have to do is figure out where these two intersect each other. So I'll adjust the sketch in just a second. Let's figure that out first. Let's figure out where those two meet. So if we set those equal to each other, what do we end up with? 3x equals negative 3. So x equals negative 1. So that's where they should meet. And they should meet at negative 1, comma 0. So let's negative 1, comma 0. So muscle mouse, like that. So this point right here, that's negative 1, comma 0. All right, and then this point over here, not that it's going to matter. That point right there is 1, comma 0. All right, now we're good to go. We know which curve's on top. We know which curve's down below. We know that we should be choosing a vertical element. We would not want to choose a horizontal element because then we would be subdividing our region R, which we don't want to do. So we can set up our double integral as an iterated integral. We're going to have double integral turned into an iterated integral with dy first and then dx. So dy, dx. The x limits are constant. Those are on the outside from negative 1 to 1. The inner limits, we have to look at the lower curve and the upper curve that bound our element. So our vertical element's there, the curve down below, the y value down there is negative x minus 1. The y value up top is 2x plus 2. So that's the setup. Setup can be complicated. All right, any questions on the setup? That's the most important part. The rest is more mechanical. Setup is the concept. Good? Chandler?
Are you going to have area that's canceling out?
Well, but think about the fact that we're dealing with a surface that sits on top of that. So, right, the fact that the domain goes below the xy plane, or excuse me, goes below the x-axis, that doesn't have anything to do with what the surface is doing.
Okay.
So the surface may or may not go through that region below the xy plane. So when we look at that surface, would that ever go below the xy plane?
No.
Because this integrand is always non-negative. So the closest this ever does, it touches the xy plane, but it's going to be above the xy plane at all points. So regardless of whether we're below the x-axis or above, the surface is still going to be above that region. Omar?
Could we, that outer bound?
Yep.
Can we divide that by 2 using symmetry? We'll go from 0 to 1 using symmetry and then multiply by 2?
No.
Not in this case.
So symmetry here means that we're talking about the volume symmetry. So we would have to know, our solid object is split exactly in half. And this solid object is very hard for us to even visualize. Z equals y squared. Okay, it's a parabolic cylinder. It's a parabolic cylinder, z equals y squared, but it's going to be hard for us to subdivide that solid object in a way that we're guaranteed symmetry. So usually with solid object stuff, unless we're doing rotational things, usually we don't even bother trying to think about symmetry because it's too complicated, usually.
Did you say that as soon as we start plugging functions, like our integrals have limits of functions, that it turns into a volume problem? It's no longer an area problem?
Say that once again.
That as soon as we plug functions in, is our limits of integration that we're doing a volume problem, not an area problem?
Not necessarily. What dictates whether this is an area problem or a volume problem is a combination. If you have a double integral, and if this was not here, then we'd be finding the area of that triangle.
Okay.
So if this was not here, if we had this double integral of dy dx, then we'd be finding the area of the region R.
Gotcha.
So what dictates whether it's a volume or area problem is this function right there. If you do a double integral of a function, you're dealing with volume.
Or if you just don't do a double.
Well, then you're not dealing with volume,
Right.
unless you're dealing with the volume that's generated by rotation. Because you can do a single integral of a rotated volume. Okay, so let's integrate with respect to y first. We have 1 to 1, y cubed over 3. Then these limits get plugged in. And
Am I the only one who thinks that's gonna turn out kind of nasty?
yeah, no, you're not the only one. Not the only one at all. I'm terrified right now.
Yeah, I think I'm just gonna use my
So we're gonna have
integration
2x.
function.
So we're gonna end up with this cubed minus. Yeah, we will not go through the details of this. We will just get to this final setup
Oh, where's the fun of that?
right in front of us. So everybody agree with that? Plug in our upper limit, plug in our lower limit, take the difference. That's just a one variable function of x. You all know how to integrate that. I will not give you one where you have to cube it out. You know, if you're home, hanging out, you can cube that out at home. So I will not give you something like that on a test.
Have some friends over, have a little
Have some
cube
friends,
this
have a
function
little
out party.
powwow with the
You'd be
with the
surprised.
cube. Here, you cube this one, and I'll cube that one.
It's a
I got
bring your own
12.
slide rule party.
Bring your own slide rule.
My birthday's next week.
Okay, so let's go to this one.
What do you happen to know the answer for that one off the top of your head? Or have it
0.
written down somewhere? I have 12.
It's 12.
Yours 12? I sure hope so, man.
It's 12. We can check after class.
Where are you going?
All right, so evaluate this integral. A sketch is helpful. It's more than helpful. It's
Yeah,
necessary.
why don't you write a sketch is needed?
A sketch is necessary. It's not just helpful.
It's helpful, yeah, required.
Sketch is required. So y equals root x. We know what that looks like. Y equals 0. That's the x-axis. And then y equals negative x plus 2. Y-intercept is 2, and it has a negative slope. So it's going to be tilting, negative 1 slope. So it's going to be going down like that.
Oh, it has a curve.
There we go. That's it.
Does that make it scarier?
Well, it just means that we have to figure out where the point of intersection is, and we have to use a horizontal element. It won't be scary.
The top one will be the one on the right.
So, yes, exactly what he said. So the top curve here is going to be the right curve for the horizontal element. So let's figure out our point of intersection. We have root x, and we have 2 minus x. We want to know where they intersect. The way we do that is to square both sides. Subtract x, factor, blah, 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 you get x equals 1.
Wow, alright, cool.
Okay. We know that
Blah, blah, blah.
blah, 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 1 or 4. So how can they intersect at 4? Did I factor right? Square, what's that called? Somebody said it. When you square both sides of an equation, you can get
Positive or minus.
an extraneous root. Did you say superfluous?
Superset?
Super what?
You said a superset earlier.
Super, but not superset. But it's not a superset. It's just you get those extraneous roots when you square both sides. So that's an extraneous solution, right? If you plug that back in, it doesn't satisfy the original, so they call it extraneous. Or superfluous, I guess. So that's extraneous. Does everyone understand that idea? Right?
Oh, so you're saying like if you plug 4 back in, you're gonna get 2 equals -2.
Which is false!
Very false.
Very false.
Okay.
Are you sure?
Very false. Very false.
But if you plug 1 in, then you get 1 equals 1. Yay.
Yeah, so it works. So anytime you have an equation and you square both sides, you have to be careful. How many solutions does this equation have? 1. You square both sides, you now have an equation that has 2 solutions. So.
Wow.
It's so mysterious. Magic. It's magic. Oh boy. The mysteries never end. The mysteries just get deeper and deeper. All right, so horizontal element. So the y's are going to be on the outside. They're going to come from the constant interval 0 to something. So y is on the outside. X is on the inside.
Oh, is that because we have a horizontal element?
Horizontal element.
That makes so much more sense.
That horizontal element, the length of that horizontal element is the right x value minus the left x value. So we need to write the equations for these functions as x values. So this is going to be x equals minus y plus 2 for that diagonal line. And what is the x value for this curve here? X equals y squared. We write it as an x value. So the length of that element, so we're going to put the lower x value down here. We're going to put the upper x value over here, or from left to right, I should say. Left to right.
That's not
Oh, did I miss something? Oh, that's Watton. Oops. Put the 2 in the wrong place. Minus y plus 2. That's better. All right, so what about the y limits? So 0 and 1. Now, it's not 1 because of this one, right? We have to plug it into that function or that function to get the y value is also 1.
Which function do you have to plug it into?
So we set this one equal to this one, so we can plug that into either one of those to get the corresponding y coordinate. And now we have a pretty simple function to partially integrate. Integrating with respect to x. Now here is one of those situations. We're integrating dx, right? The 12y is constant. The 12y is constant, so we get 12y multiplied by the length of the interval, which is the upper limit minus the lower limit.
So it just comes along to the right.
This one's just easy because instead of putting in an x, you already know what it's going to be. So you might as well just throw in the limits or throw in the bounds.
Mm-hmm. Right, so if you integrate dx, you get x. And that is upper limit minus lower limit. So upper limit minus lower limit goes right there. And then we distribute and integrate. So we end up with, if I put it in descending order, we get minus 12y cubed minus 12y squared plus 24y. So integrate that. Oh. Yes. Zero, nothing. We get 12 minus 7, 5. That is the volume between the surface and that region. Volume. Confused? So good.
Wait,
Do you have a question?
No, I'm just like trying to figure it out.
Okay. So plug it in the 1, we get minus 3 minus 4 plus 12. Plug it in 0 gives nothing. Yeah.
So, are we ever gonna have a problem where it's gonna give us the region, not where it's just gonna be like where the curves intersect?
Very rarely.
It's the same terms you just put out.
Very rarely. Yeah, I just wrote this in descending order.
Yeah.
That times that, that times that, that times that.
Yeah.
Yeah. Okay. Descending order. Descending. Okay. Another sketch. So y equals 1.
Wait a second, why is condescending called condescending? It's like, does that mean that when you're being condescending, you're going upwards?
Wait a second.
I don't,
Hold on.
contrary to ascending?
Yeah.
Contrary to descending?
Wait, condescending. So
I'll have to ask my wife. She's the English person.
Wow.
Oh, to ask my wife.
Condescending. Condescending.
I'm not even sure where you're getting from.
Where did condescending come from?
Yeah.
Well, it's an important thing.
That last surface was condescending.
Ah.
That last surface was going down. Okay, so then y equals 1 minus x. We have a line with a y-intercept of 1 and a slope of negative 1. I feel like we're back in college algebra.
I don't.
You don't? Just for a moment.
Just for
Momentarily.
just for
And
a
then
second.
positive slope of 1, y-intercept. Whoops. So I think we're dealing with something like that, more or less. So I need to stretch this guy. It looks like the region trapped is going to be this triangle above. So you always have to look and figure out what all the curves surround. Who paid that a bit? Huh. Shocker. All right, so we want to figure out the intersection point right there. Let's figure that out. So we would need to know this line. So that's going to be y-intercept. This is y equals 1. So where do those two intersect?
0.
They intersect at 0. That's quadrant 1. Quadrant 1 does not contain any points on the axes. So
How about 2?
How about 2? I like 2 better.
Okay, good.
2, 1. Set them equal to each other, you get x equals 2. Horizontal or vertical element? Horizontal. Totally obvious? Horizontal element?
Yes. So
Yes.
what was the point of finding 2, 1 then?
Yeah.
No point.
Because it's fun.
That's a lot.
Just for grins. Great question. We don't really need it, do we? Good point. Good point.
Less fun.
I just figured out I wanted to know where they met. Where those two lines meet.
So
Okay.
2, 1.
So,
Y is 0. X is 1, Y is 0.
okay, so at 0 to, I saw here the outer limit 0 to 1. The x dy. The x limits. All right, those we need to calculate a little bit. So we have a horizontal element. To figure out a horizontal distance, you do right x value minus left x value. So we need to know what the right x value is for that line. That right x value would be x equals y plus 1. The left x value is going to come from the other one with negative slope. That's this one. So that one's y equals 1 minus x. So if we write it as x equals minus y plus 1, we'll have done it. So the left x value is minus y plus 1. The right x value is y plus 1. And this one, like the last one, when we integrate with respect to x, y squared is constant, so we're integrating dx, which gives us the length of the interval, which is the upper limit minus the lower limit. So right in here, this is upper limit minus lower limit. Upper minus lower. There's upper, there's lower. simplify. Integral 0 to 1, 2y times y squared is y cubed. Looks like it, right?
Yeah.
And then we get 1/2 y to the 4th, 0 to 1. So we end up with 1/2.
I think we changed halfway through our order.
Oh, we did?
Yeah.
That
dx
sounds...
dy and then dy is still there after you do it.
So when we are doing our integral, the y is on the outside here. So that stays on the outside. So this computation in here, all this stuff right in there, that's this. There we go, that's much prettier. So if we integrate that, that gives us this. The y is still on the outside.
Well, you're doing that with regards to x, yeah?
Yep. What's the integral of y squared with respect to x?
X, y squared?
Yes. And then you plug this in for the x, and then you subtract off that plugged in for x. So that's what the upper minus lower means, is that you would have this as x, but then you plug in that and you subtract off that. So you get upper minus lower. And you'll get faster at that as you start doing it more and more. So for example, you have something simple like that. What's the immediate answer? 6 minus 1, 5, right?
Right, yeah.
Yes. Comedy of errors. All right, so that then is the volume between that triangle and the surface defined by that, z equals y squared, that cylinder. What direction is that cylinder extruded in?
The x. It's on the x-axis.
Does everyone understand that? So we know we have a cylinder when one of the letters is missing. So if we have z equals y squared, if there's no x in there, that means it's a cylinder. And if you graph z equals y squared in the zy plane, then you pull it in the direction of the x-axis. You extrude it in the x direction. That gives you your parabolic cylinder. So you've got a z equals y squared in the zy plane, and then pull it in the x direction.
So like you said, like whichever letter's missing, that's the axis is parallel to.
Yeah.
That's the axis of extrusion.
Same thing. Okay,
Yeah,
got
that
it.
one.
All right.
Yeah, what you said.
I understand.
That's true. Okay, volume. Use a double integral to calculate the volume of this. So the solid in the first octant, bounded by the coordinate planes and that surface. So we're in the first octant, and that is a surface that will be somewhere in the first octant, and we need to calculate the volume that sits beneath it. All right. So if we're in the first octant, and we've got this surface, if we want to find the volume in the first octant, well, it must intersect the xy plane, or they'd have to tell us where to stop if it didn't. They didn't tell us where to stop, so it must intersect the xy plane. How can we find the curve of intersection with that solid object and the, that's actually, let's call this a surface. The surface is going to define a solid object, but where do we figure out what the curve of intersection in the xy plane looks like?
We could use z equals 0.
Perfect. Perfect. So let's let z equal 0 to find xy curve. So the curve in the xy plane. So we get 1 minus y minus x squared equals 0. This we can solve for y very easily. So we get y equals minus x squared plus 1. So let's go ahead and sketch this in the first quadrant. We're going to look down into the xy plane. Minus y squared plus 1. It's going to look like this if we stick to the first quadrant. So parabola opening down, but then it's shifted up 1. And if we focus on the first quadrant, that's what we've got. So the surface is in front of the board, and it's coming in and it's passing through the xy plane right there. So this surface, this z equals 1 minus y minus x squared, is above this. But that's where it meets the xy plane. So you should imagine this is a wall. Each of these axes builds walls, and then the surface is coming through and creating some solid object.
And this one doesn't matter which one you do first, right? Because horizontal or vertical, it's going to be the same.
The only reason it might matter is that if we do a horizontal, we would need to write this curve as an x value. We'd have to solve that for x, so we'd have to take the square root, and that might get complicated.
Okay.
It'd be probably more natural to go with a vertical element here to see, and that probably will be better. Will?
Does this resemble some sort of, is it paraboloid?
The y coordinate's not squared, so it's going to be some wiggly thing, some amoeba thing, some wiggly. Okay, so we're going to find our volume. It will equal. We're going to do a double integral of our surface. So a double integral of surface will give the volume beneath the surface. Now we've chosen to use a dx on the outside. Our x limits are going 0 to 1. And then our y limits, we have a vertical situation. We need to figure out the y value at the top of the element and the y value at the bottom of the element. Well, the y value at the bottom is 0. And the y value at the top is just this parabola. Negative x squared plus 1.
Why is not 1?
Pardon?
Why is not 1?
It's one only on the axis.
Because it's changing, right? This vertical element will have a different y value for different positions. So that's why this y value has to change. As we move our element inside this region, that upper curve is changing, and so that's why we have to have it as a function. All right, now we're ready to integrate, or partially integrate. 0 to 1, integrate with respect to y. We will get y minus y squared divided by 2 minus x squared y. And that's from 0 to x, negative x squared plus 1 dx. Okay. We have to square. We have to plug that in for y, not x. That gets plugged in for y. So we're going to end up with integral 0 to 1, negative x squared plus 1. That part's easy enough. And now we have minus 1/2 multiplied by y squared. So we're going to have to square that. We get x to the 4th minus 2x squared plus 1. Let's move this a little bit. And then what's left? We have to minus off, we have to subtract x squared times y. So minus x squared multiplied by negative x squared plus 1 dx. Lovely.
Lovely.
Lovely. I don't know why I went way over there.
Not the
We need
ugliest.
more space.
Is he uglier?
True. True.
It could be worse.
Isn't that also supposed to be squared, that last bit?
I don't think so. Because we're plugging in just for this y right there. So it's negative x squared multiplied by.
Oh yeah, we're
that,
plugging into the y.
Plugging in for the y. Really easy to get tangled up on that. All right, so let's combine all our like terms here. Let's put it in descending order. So I see a minus 1/2 x to the 4th, and over here I see a plus x to the 4th. So that means a plus 1/2 x to the 4th. So we got that taken care of. So that one and that one are taken care of. And then what's next? Squares. So out here we have a negative x squared. here we have a plus x squared, right? So plus x squared, that half comes in and cancels with the 2, so we get a plus x squared, a minus x squared, so those x squareds cancel. And the only x squared left is over here, that's minus x squared. All right, x squared's taken care of. Are there any linear terms? No. Constants. We have 1 minus a half, and that's it, I believe. 1 minus 1/2, so that's 1/2. Very good. That's integrable.
Where does spare x squared come from?
This x squared?
Yeah.
So if we look up here, we have that and that canceling. Because minus 1/2 times minus 2 is plus 1x squared.
Right.
So those cancel. And then negative x squared times 1.
Ah, that one.
That's the only one that's preserved. All right, so our volume is 1/10 minus 1/3 plus 1/2. 1/10 minus 1/3 plus 1/2. Whatever number that's equal to.
4/15.
4/15. Thank you. Beautiful. 4/15. It's pretty nice.
Not bad.
4/15. All right, so that's, you're doing great. You guys are rocking it. Wow. You guys are going to have such a good weekend. Okay. Oh, there's another one. We better do it. Okay, so the solid beneath the cylinder is equals y squared. What letter is missing? X. So you extrude parallel to the x-axis. Can you visualize that cylinder?
Yes.
Yeah.
We drew it in class like a billion times.
Can you see it? Can you see it?
I'm more of a dig it kind of guy.
Can you dig it? I can dig this one. This one's pretty good. So we look at the z-y plane, the y-z plane right there, and z equals y squared is going to be this parabola. And then x is missing, so we're going to pull it in the x direction. So this is going to be very hard to draw with this cramped space, but that looks perfect. Or maybe not.
Amazing.
Absolutely
You drew it way
amazing.
better in the other one.
We need more space. We need more space.
You did it great in the cylinder notes.
Yeah, in the cylinder notes it looks
Wow, that's
really
where it
good.
was from.
Yep.
Knew it.
Yeah.
In the cylinder
right?
notes,
Oh,
it's
great.
Where's your test?
I messed up.
So that's not too bad. You can see that, right? All right, so parabola in the YZ plane, and you pull it in the x direction, giving you this parabolic cylinder.
I get the feeling we should somehow do something to connect the bottom part of it as well.
Yeah, that sounds sketchy.
Yeah.
There. Okay, so the volume then on our interval, let's see if we can get our limits correct. Our surface is pretty easy. It's just y squared. Then we have to decide on our limits of integration. So
the region.
yeah, let's take a look at the region. So let's go down to the xy plane. And they're telling us that we're going to go between 0 and 1 for the y values. So 0 to 1 on the y-axis. 0 to 1. And then in the x, let's see, what's going on over here? So x is between y and 1. So x equals 1 is right there. Y equals x is this line right there. So which side of that line are we on?
The bottom side.
So the x values are going between x equals y and x equals 1. So that's going to put us in this Very suspicious. So it's going to put us right in here. That'll be our region. And vertical or horizontal element? Yeah, in this case it doesn't. In this case it probably does not matter a lick which way we go. Probably going to be. Generally, if it doesn't matter, we go vertical just because it's a little easier for us to conceptualize it, but probably it's not going to matter at all in this case. So the x is going to be on the outside, 0 to 1. And then the limits for the element, the lower limit is y equals 0, the upper limit is y equals x. So 0 to x. Do you agree with those? So we need vertical distance, y values, so we have to find a y value for the top, a y value for the bottom, y equals 0, y equals x. Integrate that with respect to y. We get y cubed over 3 from 0 to x dx. So we get the integral from 0 to 1 of x cubed over 3 minus 0. So we get x to the 4th over 12 from 0 to 1. So we get 1/12. That will be our volume. So if we're looking down here in the xy plane and trying to draw that triangle, why am I even suggesting this? We're dealing with something, you know, that triangle is down here in the, kind of like that. And we're looking for the volume that's just sitting underneath that parabolic cylinder and above that triangle. Cool? You ready? Pictures. They've given us pictures.
Like in the picture I'm seeing for 57.
For 57? Okay, how about, do you like this up here? Reverse the order of integration. Okay, now the nice thing is that they've told us one direction. They've given us one order, and now they want us to reverse it. And they've told us everything. They've drawn the graph of each of the limits of integration. Now the function is just abstract. We don't know what it is, but you're imagining a surface on top of that region. And what direction did they integrate? What direction is their element? So they used a vertical element, having that x on the outside. That's a vertical element. So we want to switch it. All right, so let's try. So to switch this, let's see, where can I write it? Let me move that one over. So if we want to switch this, we want to use a horizontal element. So we're going to have an element that way. And we are going to end up with the double integral. Whatever this function is, we're going to go dx dy instead. Let's go with the outside limits first. What should the outside limits for y be? 0. The outside limits? So 0 to 4. So the outside limits are the constant limits. So you're imagining this horizontal. You're imagining this horizontal element moving all the way from y equals 0, and it goes all the way up to y equals 4. So this horizontal element ranges from y equals 0 to y equals 4. So that's why our limits are 0 and 4. How about our inner limits?
Go from y to square root of y.
So we have to be a little careful there because we need x values. When we are finding a horizontal distance, we need to have the left endpoint and the right endpoint written as x values. So this one is going to be x equals the positive square root of y. And the x value over here will be x equals y divided by 2. So now we have our inner limits. We have to go from left to right for inner limits. So we're going to go y divided by 2 over to square root y. So that's our setup. Now let's try this one. same idea here. They've done it with a vertical element. We want to say, nope, we're going to go horizontal. And our outer limits, what will our outer limits be?
0 to 6.
0 to 6. So we're going along the y-axis. There is a horizontal element for all y values between 0 and 6. Inner limits, we need to have the endpoints of this element be written as x values. We need to find the x value of the left and the x value of the right. The x value of the left is just 0. The x value of the right, we're going to add 2x to both sides, subtract y, divide by 2. And usually we write it in descending order. That would be our x value there. The limits of integration then are 0 and negative 1/2 y plus 3.
And that wouldn't matter though, right? If you used vertical or horizontal in that case?
Right. In this case, it's the only thing that might come into play is what this function looks like.
Okay.
So according to the region, it's very easy to set up either for both of these. And so then the integrand would be the consideration if maybe one is easier than the other. I think we should probably do one more. Yeah. Sounds good answer. Sounds awesome. Endless well of enthusiasm.
These make sense. Let's keep doing that.
All right, let's not stop. Let's not stop.
Sense.
Sense these make. All right. Integrate with respect to y, that thing. Ooh, can't do it. Right?
What?
You can't do it. You can't do it with respect to y. Do you agree? So if you let u equal y squared, then du is 2y dy, but there's not a y on the outside. So we can't integrate this with respect to y first. So we have to switch it. So let's take a look at our region of integration. So when we look at our region of integration,
It's a rectangle.
no,
No,
it's
it's
not
not.
a
No, it's
rectangle.
not. No, it's not.
Heavens to Murgatroyd.
Heavens, what?
That was a cartoon when I was a kid. All right. So the x values go 0 to pi, but the y values go from y equals x to y equals pi. Y equals x looks like that. Y equals pi looks like that. So this one is y equals x. This one is y equals pi. So y equals, we started at y equals x, and we went up to y equals pi. So this is our region of integration in here. And they used a vertical element in there. So we want to switch to horizontal. We're going this way. So we are going to switch it up. We're still going to have the same integrand, except we're going to have a different order of integration. The x's are going to be on the outside, excuse me, the y's are going to be on the outside going 0 to pi. The x's are on the inside. The x value on the left is x equals 0. The x value on the right is x equals y. So 0 to y. Now, when we integrate this with respect to x, we get, there is no, right? There's no x in here, so we just get the length of the interval. So we're going to end up with y multiplied by sine of y squared dy. Right? So there is no x. So that means that the effect of that inner integral is to multiply by the length of the integral. The length of the interval, I should say. So y minus 0 is y. Now we're golden. Now we can let u equal y squared. Du will be 2y dy. We can substitute. So we have integral y dy is going to be du over 2. And if we want to switch our limits of integration, plugging in a y equals 0 gives a u equals 0. Plugging in a y equals pi gives a pi squared for u. Integral of sine is minus cosine of u. Whoops, not pi over 2. Pi squared. What a strange limit. All right, plugging in pi squared, we get minus 1/2 cosine of pi squared minus cosine of 0. So we end up with that.
Is the minus a half?
Pardon?
Is the minus a half?
What about the minus 1/2?
That's the idea. Oh, no, minus a half. I see.
Yeah, I just put it on the outside and then cosine top minus bottom. Any questions on that one?
Say it again with why we used the first integration was we went to y sine y squared.
So here we're switching, so we have the same exact surface in here. And we're switching because this we can't integrate with respect to y.
Right.
If this was just y, we could integrate, or if there was a y on the outside, we could.
Right.
But we
Right.
can't. So we switch to x, and when we integrate with respect to x, this is just a constant. So it comes down. And then the integral is x, and you plug in the y and you plug in the 0, so you get y minus 0, which is where this y comes from. And then we use substitution from there.
Wow.
Thank you.